my network-attached storage has supercharged my productivity for all of my machine learning experiments and projects. My ML server only has a measly 2 terabytes of storage, so using the 16 terabytes for my NAS to save checkpoints or load datasets during training, or caching open source weights I'm downloading for inference or fine-tuning has become a no-brainer. Today, we're going to set up my favorite use cases on my NAS, like experiment tracking with weights and biases, our own proxy caching servers for Hugging Face, Ollama, and PyPI, and finally, efficient data loading with a neat little Python library called WebDataset. To showcase how lightweight and simple the setup process for each of these services are, I'll take you guys along for the ride with this little Zimaboard. You can follow along with any machine that has Docker installed and a good amount of storage. Since I want to get to the exciting machine learning stuff ASAP, I'm going to breeze through the build and setup process for the Zimaboard. Also, frankly, this is not a long-term solution with the two 256GB SSDs I'll be using. My main NAS has 16 terabytes of usable storage. The Zimaboard's simple Intel Celeron N3450 and 8GB of RAM are not the limiting factor here. In Proxmox, I just set up a ZFS pool, create a lightweight LXC container with its virtual hard disk on the ZFS pool, and install Docker in the container. Just a bare minimum for what we'll be running today. At the end of the day, all you need is a host that is capable of running Docker to follow along. I'll revisit some of the nuances with Docker and mounting your NAS towards the end of the video that might be relevant to your setup. However, after my LXC container is set up and I run docker ps-a, I can see that we're all ready to go. Our first stop is actually my favorite on the list, which is why I couldn't leave it for the end: weights and biases. Random side note, this video isn't sponsored by them or anything, but I love this cute little plushie I got at their conference earlier this year. Gone are the days where I have to print out my loss curves or manually create matplotlib graphs to see if my model is learning. WANDB is an experiment tracker where you can log your training run's important metrics and hyperparameters, along with the generated images or videos in one neat centralized location for easy comparison between runs. It's a service that many big companies and startups use, and it's become invaluable. You can also upload and download checkpoints with WANDB seamlessly, another reason why having it on our local network is such a boon. Depending on what you're training or fine-tuning, these PT files could be multiple gigabytes, and a managed version of WANDB only gives you 5 gigabytes of storage. And if you run it directly on your server, your training run will crash when your server inevitably runs out of disk space. Thankfully, our NAS comes to the rescue here. Setting up WANDB is as simple as using Docker Compose to run this specific Docker Compose file. Just make sure to modify the host and variable with the IP address of your Docker host. After running Docker Compose up and waiting for a couple of minutes, we can navigate to the IP address of our Docker host with the port the WANDB container is listening on to be greeted with the WANDB login screen. This is to create a local account, so feel free to put in any information. Just make sure that you don't forget the password. After logging in, we'll need to activate our WANDB instance, which we can easily do by clicking the Get a Free License button and creating an actual WANDB account. I know, it's actually kind of annoying, but I really like WANDB's user experience over other open source alternatives like AIM or MLflow. After authentication, you'll be prompted to create a new org, just disable the free trial stuff, and then copy your license key. From my experience, your online WANDB account and your local instance are separate, so you can just recreate your online account whenever you need a new key. Afterwards, you'll be redirected to your local instance. Just add the license key and your local instance is ready for its first experiment. Make sure you note down your WANDB's URL and the API key given to you on the home page. I've already removed my instances before you see this video, so don't mind my API keys. Not to mention that this is all on my private home network anyways. Let's quickly jump over to Cursor to see the code that we'll be running today. First, I add the WANDB base URL and WANDB API key values to my environment, but feel free to add them to your bash RC. Running WANDB login -- verify confirms that things are working as intended. But before we run a sample training run, let me show you the actual changes that are necessary to any arbitrary training script to add WANDB support. I'll be using my neural radiance field training code from last year. If you want to learn the theory behind what we're doing here, definitely check that video out. But at a high level, all we need to do is call the WANDB init method at the top, which returns a run object. We also pass in all of our experiment's hyperparameters here so WANDB can track them for us. This makes comparing results across runs incredibly helpful. Then, to log our loss, we just call run.log and pass in a dict of values we want to track. It's really that simple. The image and checkpointing code might seem a little scary at first, but for the image, we just pass in the torch tensor into the WANDB image constructor and log a list of these WANDB image objects. For the model checkpoint, I like to use a temporary file to save the checkpoint and then create a WANDB artifact object. I then add the temporary file to the WANDB artifact and log that. After the checkpoint is uploaded to our WANDB server, the local copy is automatically removed, saving space on our local machine. Let's run this script now. As the script starts, we see that it gives us the URL where we can monitor our run from. Clicking on it shows us our loss curve and generated images for however much the training has progressed. Our graph continues to update as training goes on. After training has completed, we can see the progress our model has made. Our checkpoints are also saved in the Artifacts tab. Let's load one up for inference. They give us the sample code to do so. This second notebook loads a checkpoint and renders a video of our neural radiance field spinning around, which also gets logged back to WANDB. Another fun fact is Hugging Face's Accelerate library also has built-in support for WANDB, which makes monitoring multi-GPU runs much simpler. This is where other automatically logged metrics like GPU utilization and fan speeds come in handy. While Accelerate is out of the scope of today's video, let me know if you want to see a future video about that. Now, let's move on to another huge pain point that my NAS solves for me. Running out of space when trying out so many of these cool open source models, and it seems like a new one's coming out every single day. Each of these weights can be hundreds of gigabytes. And not to mention, what if you want to compare their performance between two machines on your home network? Downloading everything twice is quite redundant. That's why we'll be setting up this open source caching proxy for Hugging Face called Ollama. Since it's just a Python package, I created this Docker file that sets up the Python environment and runs the Ollama CLI. Then I use this Docker compose file to spin up the container. Again, note the port that the container will listen on. After running it with Docker compose up, it's super simple to use the proxy. All you need to do is set the HF endpoint environment variable to the IP address of our Docker host and the port number we just noted. This value needs to be set for all devices on your home network. I'd recommend just updating your bash RC so you don't have to set it every time. Now, if you use the Hugging Face CLI to download any model, it'll first check the cache and then download it from Hugging Face. This first download for GPT-OSS 20B on my ML server took over 20 minutes with my 300 megabit internet connection. But when I download it for the second time on my gaming PC, the download fully saturates my 10 gigabit home network, which is about 33 times faster. Fun fact, vLLM, a very popular inference library for LLM inference, downloads its models from Hugging Face as well, so those downloads will also be cached. The premise behind a PyPI proxy is also similar to the Hugging Face proxy. I mean, PyTorch wheels aren't getting smaller anytime soon. This is the repo I like using. I just used the following Docker compose file with these environment variables set, which affects some caching behaviors. I encourage you to read the repo's readme for your own requirements. In order to use this, I can use the -- default index flag or the UV default index environment variable for UV installations. Originally resolving and downloading the dependencies of my neural radiance fields project on my ML server took a couple of minutes. Now let's run uvsync -- frozen on my gaming PC. Looks like our caching works. The second time around, downloading the packages only took 15 or so seconds. Additionally, you can check out Sonatype, which is a caching service that has a free community edition with support for Hugging Face and PyPI. It might be a little bit more robust than these GitHub repos, but I'd encourage you to experiment. There's also an Ollama proxy I love using that I'll link down below. The setup process is pretty much identical to these other two proxies. Spin up the Docker container, grab the IP of your Docker host and the port the container is listening on, and set the appropriate model URL in Ollama to point to the proxy from any device on your home network where you want to use the proxy. These caching proxies are an amazing way to utilize all of the space on your NAS. You can just delete the local copies of these models when your main system fills up, and re-download them from your NAS as necessary at blazing fast speeds. The final thing for today's video isn't a Docker service, but rather a Python library, WebDataset. As datasets continue to grow in size, it may be limiting to try to fit all of them on your server's local storage. But a huge limitation of any storage over the network is that random reads and writes for small files is incredibly slow. This is why it's a horrible idea to just copy a directory of files over to your NAS and then point your training job to the remote directory. Moving around tarred files is much faster because the file system sees them as one large contiguous file. WebDataset exploits this property by working directly with tar files. For each training example, the names of all of the files need to be the same minus the extension. That's how WebDataset knows which files each training example consists of. You can store any regular file like images, text, or even audio. Then, during training, WebDataset will stream in the data over the network as an iterable PyTorch data loader. Let's say I have this synthetic dataset of a bunch of flowers that I may want to use to train a simple image generation model. All I need to do is simply store them in a tar file. I use WebDataset's shard writer class to automatically split up the giant folder of images into shards of 10, 24 images. This is a value that you can play around with. Then, in this sample Python script, I just create a WebDataset object and iterate over the data loader. When the files are local, iterating over 100 batches takes about 11 seconds. But with them on my NAS, it takes around 35 seconds, which is indeed unfortunate. But don't freak out, because when we actually run a training job, the network latency is hidden with data prefetching via multiple data loader workers and the time it takes our GPU to actually perform the training loop. In both cases, we can see that training progresses at about 6.5 iterations per second. There's one small note I want to make. Throughout this video, I use Docker volumes because they're really simple and portable. The entire virtual hard disk of my LXC container was on the ZFS pool I created with Proxmox, so that means the Docker volume would automatically be on my NAS. However, if you're using TrueNAS or Unraid as your NAS software and your Docker host is separate, you might have your NAS mounted on your Docker host via SMB or NFS. If you're in the second camp, you'll probably want to use a bind mount to pass in a directory from your NAS's mount point on your Docker host to the correct directory in your Docker container. I'll leave the correct paths in the description below for each service. But take weights and biases for example. In the Docker volume, it has a path for some metadata and the SQL database, and another path for its internal min.io service it's running for object store. I recommend only putting the min.io on my NAS so the database remains on local storage for the sake of speed. It's funny because using an external object store instance requires the paid version of WANDB, but we're able to alleviate the need for that via this hack. Also, I'd recommend using just NFS instead of SMB because that's native to Linux, and some containers require specific ownership of the directories you're passing into the container. Like the UID of the main user in the weights and biases container is 999, and if the chown command fails, the container doesn't start up. I had to find that out through a lot of trial and error, so hopefully that makes your guys' lives a little bit easier. There you have it, guys. I honestly cannot overemphasize how incredible it's been to have a centralized storage solution for my multiple machines to all connect to. Even if you don't have a 10 gigabit home network, a 1 gigabit network will still be a major boost to your productivity. Anyways, thank you guys so much for watching, and as usual, if you have any questions or comments or want more in-depth tutorials for anything that we covered today, please let me know down below. Until next time though, bye-bye.